Hello and welcome back to Lesson 2. In the last two parts of this lesson, we revised using momentum equations and examined how to obtain estimates for pressure drop and volumetric flow rate for tapering geometry. We called this approach the lubrication approximation as it originally stems from tribology. What I'd like to do now is examine solutions of the Navier Stokes equations for ducts that have a constant but non-circular or non-planar cross-section. We're not actually going to derive these solutions, as this is a polymer processing course and not a pure fluid mechanics course, but the results that we'll highlight may be of use to estimate, or perhaps elucidate, certain aspects of polymer processing flows. So, let's start by examining what sort of flows we might be talking about and what sort of products that result from these flows. So, in the introduction to this lesson, we talked about making polyester yarn, and we said there's all sorts of different polyesters that you can use, but the core process, that of melt spinning, is going to be the same for either. So the melt spinning process started with extrusion to produce a polymer melt. That melt was then stabilized in terms of volumetric flow rate by a metering pump, which in turn fed a big shower head, or something that we liken to a shower head, which we call spinnerets, and out of the spinnerets came the fibres that were then quenched and processed further downstream to increase orientation. Okay, so we didn't actually mention what shapes these little channels in the spinnerets took. We likened it to a shower head, but didn't really go any further. Now, if one looks in the patent literature, one will find a very big variety of different cross-sectional shape for spinnerets. Now, the reasons why the spinnerets can take different shapes are many and multiple. So, for example, if you've got a viscoelastic polymer, it's going to swell slightly as it leaves an extrusion nozzle, and all these spinneret exits are extrusion nozzles. And so a lot of these shapes may be limiting the extent of, for example, extradate swell. But what we can see triangles, we can see squares, we can see lobed type shapes like a clover leaf. And so the flow field in each of these different shapes isn't going to be the same as a flow field through a circular cross-section. So there may be a use for being able to estimate shear rates and sometimes pressure drops in these non-circular cross-sections. So let's have a look at how we might do that, and I'm going to introduce a very, very useful resource in the form of a book. So this book by Michael DeVille, the Introduction to the Mechanics of Incompressible Fluids, is open access, which is fantastic. It's limited to Newtonian fluids, but it does give the mathematics underlying the solutions I'm going to present in this part of this lesson. The particular details for this part of this lesson are given in Chapter 3 of this book, which is entitled Exact Solutions of the Navier Stokes Equations. The wonderful thing about this book is it's very, very widely available due to it being open access, and I've popped a copy for you on Canvas. So, let's start with the simplest departure from a circular cross-section, which is that of an elliptical cross-section. So we may have a squashed duct, a squashed circular duct, that takes the form of an ellipse, having a semi-major axis of length A and a semi-minor axis of length B. Now, we can describe the shape of an ellipse using those semi-major and semi-minor axis dimensions, and the equation of ellipse appears there on the board. X over A all squared plus Y over B all squared equals 1. So it is possible to solve the Navier Stokes equations using a substitution for an ellipse to achieve this result for the z direction velocity. So let's just have a little look at the form it takes. We've got delta P over 2 mu L. Okay, that's a familiar term. It's a pressure drop per unit length and taking into account viscosity. And then we've got geometric terms. Now note that we've solved this in Cartesian coordinates because that is a more convenient coordinate system in which to describe an elliptical geometry. Now the wonderful thing with this result is we can describe the variation of the axial velocity Vz as a function of x and as a function of y. We can easily differentiate that result. And of course that will give us an idea of the shear rates across this shape, which may be very useful because we know that shear affects orientation and orientation affects mechanical properties. So it may allow us to estimate, and again I emphasize the word estimate, some orientation that might be developed as a result of the flow in the melt phase through a channel of this cross-sectional shape. For an ellipse, it's also quite nice because we can actually also work out what the volumetric flow rate is, which in turn will allow us to work out what the pressure drop is. So there's the result for the volumetric flow rate of a Newtonian fluid through an elliptical cross-section duct. This is described on pages 82 and 83 of Deville. And of course, we always want a sanity check. We want to make sure that there isn't an error. So if we look at that volumetric flow rate expression, if we set A equals B equals our radius, big R, making the analogy from an ellipse back to a circle again, we retrieve the expression that we're familiar with for a circular cross-section duct. Okay, so now let's move to a slightly more exotic geometry. Let's move from an ellipse to an equilateral triangle. So our triangle has the dimensions that I've shown there on the whiteboard. There is an equation, believe it or not, that describes the equilateral triangle in Cartesian coordinates, and for interest I've put that on the board too. Again, we're not going to go through the steps that are used to get to the results of the Navier Stokes equation for flow in a triangular cross section. I shall simply quote the result I've put on the board. We have an expression that allows us to calculate the axial velocity, and again this is differentiable with respect to x and with respect to y, which will allow us once again to work out the shear rates across that cross section, which may be of use. Finally, let's look at flow in a rectangular cross section. Now you might come across all sorts of rectangular cross sections in terms of ducts in polymer processing, and if we think about film casting, the exit of a film casting die is going to be a rectangular cross section. So let's have a look at an arbitrarily shaped rectangle. Let's say we've got a width of 2a and a thickness of 2b, and what we end up solving now is this equation here. So we can reduce the Navier Stokes equations down to just having one velocity, an axial direction velocity, a velocity in the z direction, changing as a function of x and changing as a function of y. And our key pressure drop is only occurring in the z direction. And so this is a separation of variables solution to that partial differential equation. The result of which is quite large, and I've written on the board there for you. And again, we can see that this final expression for Vz is a function of x and a function of y. So we can differentiate this, so we can get the shear field across this shape. And again, that shear field can give us some very useful information about what might be happening to the fluid in terms of stress, in terms of strain rate, maybe orientation, as it flows through a duct of this shape. And this solution is detailed on pages 83 and 84 of Deville. Let's recap a few key points. So we've seen, or the crux of this lesson was to demonstrate, that it is possible to solve the Navier Stokes equations for two-dimensional shapes. And I'll call those shapes of complex cross-section because they're more complicated than a one-dimensional shape. We've had a look at three results. We haven't looked at the derivations, but I've given you the reference for the curious to have a look at. We've looked at results for elliptical cross-section channels, equilateral triangularly shaped cross-sectional channels, and rectangularly shaped cross-sectional channels. The key thing with these results is that they give an expression for the z direction velocity. For the elliptical channel, you also have a volumetric flow rate, which is useful because you can use that to calculate pressure drops. But even if only you've got a z direction velocity, you can still differentiate that with respect to x and with respect to y to get your shear rate profile. Sometimes you might have to find volumetric flow rates numerically for more complex shapes, but those shear rate profiles may give you some useful insight into what might be happening to the fluid as they go through these more exotically shaped flow channels.